In order to accurately measure the efficiency of an algorithm, we first have to clearly establish the absolute boundaries of its overall performance. Up to this point, we've relied on big O notation. That gives us our upper bound, the worst-case scenario, or the maximum possible growth rate. In the previous part, we've also defined omega notation. That provides the lower bound, showing us the best-case scenario, or the absolute minimum growth. But designing software requires more than knowing the extremes. If you only know that a train trip takes between 1 hour and 10 hours, you can't accurately plan for its arrival. To close that gap, we use theta notation. Theta represents the tight bound. It defines the exact asymptotic growth rate of an algorithm. This tight bound exists when an algorithm's upper bound and lower bound share the same order of magnitude. When the worst-case and best-case scenarios converge, the algorithm can be classified by a single specific rate of growth. To prove this convergence, we need to look at the formal mathematical definition. A function f of n belongs to the theta of g of n if it is trapped between two scalar multiples of that base function. Specifically, c1 times g of n is less than or equal to f of n, which is less than or equal to c2 times g of n. This condition only needs to hold true after a certain minimum input size, which we define as n sub 0. We can visualize this bounding effect on a Cartesian coordinate system. This central line represents the actual execution time of our algorithm, f of n. We then plot our two constraints, the blue line for the lower bound and the cyan line for the upper bound. We identify n sub 0 at the point where the algorithm's performance becomes permanently locked between these two limits. Once the algorithm is mathematically trapped between these two scalars, its performance becomes predictable as the input size approaches infinity. Let's apply this to a concrete linear function, 3n plus 5. For the upper bound, we can prove that 3n plus 5 is less than or equal to 4n for any input size of 5 or greater. This gives us a big O of n. For the lower bound, we see that 3n plus 5 is always greater than or equal to 3n. This establishes an omega of n. Since the big O and omega bounds match, we conclude the tight bound is theta of n. This methodology scales to higher polynomials, such as the quadratic function, 4n squared plus 2n plus 1. Calculating the inequalities for this function results in a matched pair of O of n squared and omega of n squared. With the upper and lower bounds in agreement, the exact asymptotic trajectory is theta n squared. In any polynomial, proving these two matched limits determines the definitive growth factor. While inequalities are useful for proofs, analyzing complex code requires a faster approach. To find the theta bound quickly, we follow 3 steps: remove the constants, keep the highest power, and ignore all lower-order terms. Under these rules, simple operations translate to theta of 1, while a single loop over n items becomes theta of n. We can apply this to more complex code, like this nested triangular loop, where the inner loop's range increases with each iteration. Tracing the execution, we see that the total number of operations builds row by row into a triangular pattern. This geometric pattern represents a summation series, 1 plus 2 plus 3, all the way up to n. The formula for this sum is n squared plus n, all divided by 2. We apply our extraction rules. We remove the constant division by 2 and ignore the lower order n term. This leaves us with a tight bound of theta n squared. This perfectly demonstrates how the underlying growth of a software loop is tied directly to its mathematical structure. We can apply this analysis to evaluate the complexity of standard algorithms. For instance, accessing an array index is theta of 1. A binary search is theta log n, and merge sort is theta n log n. Asymptotic analysis also applies to the memory an algorithm consumes, or its space complexity. A few integers represent constant space, or theta of 1. A one-dimensional array is theta of n, and a two-dimensional matrix scales at theta of n squared. Big O and omega define the ceiling and the floor of performance. Theta notation combines these into a single tight bound. By identifying a theta bound, we establish the definitive rate of growth for an algorithm, allowing us to predict how performance scales as inputs increase.